This is the last lecture on substitution reactions. But before we actually go into this lecture, let us do a quick review of what we did in the last lecture, or what we covered in the last lecture. We covered essentially SN2 reactions, which are described as bimolecular, where two reactants, the nucleophile and the electrophile, come together in one step to form the product, of course after going through the transition state. We also looked at the effects of the solvents on these reactions. Even though they prefer to have solvents that are aprotic, if there are solvents with different polarity, these solvents can actually affect the rates of these reactions. Next, we looked at the substrate or the electrophile, the structure of these, and that we decided that, or concluded that, the tertiary was least reactive, and the primary or the methyl was the most reactive in terms of the SN2 reaction. We looked also at the electrophile, and don't forget the electrophile has to gain access to the electrophilic carbon, which means that the electrophile must be small. And in addition to being small, must not be basic, because if the nucleophile is very basic, there will be elimination reaction, which we'll cover in the next lecture. We looked also at the stereochemistry of the products, and the bottom line here is that there is inversion. That's inversion of configuration around the chiral carbon of the product. And lastly, we looked at some experimental results and how this information covered in that lecture can be used to explain these experimental observations. That is an important aspect of organic chemistry, is the use of these concepts to explain experimental observations. Okay, let's begin. So in this lecture, we will cover aromatic substitution reactions. This time is aromatic. So we'll look at the mechanism for one type reaction called the electrophilic aromatic substitution reactions. And then we look at the applications. Of course, you know, I emphasize the applications of concepts to explain different experimental results. Next, we look at an important aspect in chemistry, especially organic chemistry, and that is the kinetic versus the thermodynamic control of reactions. Especially if you're in research, a lot of times you will need to carry out reactions under different conditions to get desired products. We'll cover that here. And lastly, we'll cover the nucleophilic aromatic substitution reactions. So this is a different mechanism for aromatic substitution reactions. Okay, let's begin. So in terms of the electrophilic aromatic substitution reactions, here is the general format that you're familiar with. We have the benzene ring. We have here E, which is an electrophile. As you will recall, E plus electrophile is an electron-loving species. So here we have a substitution, and the substitution involves here H is being substituted with E plus to give the substituted benzene here, or the substituted organic product. So we have different ways of creating the electrophile, or different reaction conditions of creating the electrophiles. Of course, since the benzene ring here is nucleophilic and unreactive, or very stable because of the aromaticity, catalysts are required for these reactions to occur. Here is the nitration of benzene. It requires nitric acid in the presence of sulfuric acid to create the nitronium electrophile. So this would be the NO2 plus electrophile that's generated from this mixture here. Bromination requires the bromine in the presence of iron bromide, and of course the active electrophile here is Br plus. Same here, Cl plus. Notice again the electrophile is needed to create these very reactive electrophiles. You may recall the Friedel Crafts alkylation. Here is the alkyl halide and the catalyst, aluminum trichloride, and the active electrophile here is the carbocation. And over here the acylation, the active electrophile here is the acylium ion, or C double bond O, and of course typically an R and A plus. So these are the reactions that you covered in undergraduate organic, and these are the electrophilic aromatic substitution. What we'll do here, however, is to review the mechanisms. The first mechanism here, or the under mechanism for the electrophilic aromatic substitution, is shown here, where we have in the rate determining step, electrons from the benzene ring attacks the electrophile, because the electrophile is positive, electrophilic, to create here a resonance stabilized intermediate, or the benzenium ion. Notice it's resonance stabilized as shown from these different resonance structures, but these are the resonance structures of the intermediate. One intermediate, but just to illustrate the electron movement is shown here through resonance. In a fast step, the product is created. So that is the mechanism, the rate determining step, which destroys the aromaticity, and the fast step, which regenerates the aromaticity. Here is the energy profile representation. Of course, as you know, in chemistry, we communicate a lot using diagrams and figures. So here's a diagram that represents that concept we described before, or the reaction mechanism. In the rate determining step, the reactant goes to the intermediate. In doing so, this is the energy of activation right here. As you can see, that's pretty large. So that's why that determines the overall rate of the reaction, the rate determining step. In a fast step, the intermediate goes on to form the products, and you will notice here is the energy of activation, pretty small or much smaller, and that is why this is described as the fast step of the reaction mechanism. Let us look here at substituted benzene. So a lot of times you will be required to carry out a reaction where we have a substituted benzene and not benzene, and this substituted benzene reacts with an electrophile. In this case, however, it's not just one product as we saw before, but there are three possible products, because the electrophile can substitute for this hydrogen as shown here, for this hydrogen here, or for this hydrogen here, which gives 3 different products. Now comes the question, how do we determine which is the major product? Because as you know, in organic chemistry, we always try to get a large percentage of one product, and that determines the percentage yield of that reaction. So let us see how we can make that determination. For this reaction, for example, if this is anisole with an OCH3 bonded to the benzene ring, if we carry out here the Friedel Crafts acylation, which is an electrophilic aromatic substitution, only 2 products are observed. In the para position, para to the methoxy group, and in the ortho position, ortho to the methoxy group. It turns out that this is the major product of these 2. But let us see why that is the major product of these 2. If we should look at this type substituent, the methoxy group, for example, it has an unshared pair of electrons on the atom that is adjacent to the benzene ring. That has the ability of pushing electrons into the ring. By drawing resonance structures, what you will observe is that the ortho and the para positions are the most nucleophilic in terms of the electrons being pushed into the ring by this type substituent here, a substituent that has at least 1 unshared pair of electrons. So that explains why the electrophile will go here or here. Of course, putting the electrophile here is the same as here, the ortho position. So that explains why 2 products. Why is there 1 major product as the para position? And that is because of the steric interaction between putting a substituent here, E plus here, and this other group that's on the molecule. So there's steric interaction in that product. So let's go back here. So as you can see here, there is steric interaction here. So that is why this is the minor product, whereas this does not have a similar steric interaction. Let us look at another type substituent, benzoic acid. If benzoic acid undergoes an electrophilic aromatic substitution, there's only 1 product as the major product, and the substitution is in the meta position. Only 1. There's no ortho substitution, or there is no para substitution. Let us look at the mechanism to try and explain why this is the major product. If there is an atom that's bonded to another atom, and it has here a conjugation, such as a double bond. This could be a carbon-carbon double bond, but if it is a polarized double bond where Y is electronegative or more electronegative than X, you can see here it has the tendency to pull electrons from the ring towards this more electronegative atom, such as oxygen, as we have seen with the carboxylic acid. So for substituted benzene that has a double bond in conjugation, notice in conjugation with the aromatic ring, the electrons of the aromatic ring can be delocalized as shown here. So that will put a positive character on this carbon and a positive character on the para carbon. So as you can see from this, the ortho carbon and the para carbon, ortho carbon, they all have electrophilic characteristics. So if this were to react with an electrophile E+, you can see that it will not go here because they are of the same charge. So by default, it will have to go in this position, or in the meta position. As a result, these type substituents are called meto-directors or deactivators because it deactivates the ring towards electrophilic aromatic substitution. The previous ones were called OP directors because it directs the incoming electrophile to the ortho and para position, but mostly to the para position, and they are also called activators. So let us use that information now to explain some experimental results. So for the Friedel Crafts acylation of benzene, a rho value of negative 9.1, notice negative, and a very large value 9 was obtained for the linear free energy relationship studies. It's the Hammett plot. So the question now is, can this information be used to justify the mechanism that we have just proposed? Or, using the reverse, can we explain this experimental observation here by a mechanism? So let's look at the observation first. So note that the AlCl3 is a catalyst. So it is just here to generate the electrophile. In this case, the electrophile is the acylium ion. It is positive. So that would imply that the nucleophilic benzene ring reacting with a positive acylium ion generates a positive intermediate in the rate determining step. In the rate determining step of this reaction. So let us see how that would work. So, as we have said, this is a catalyst, and its job is basically to pull off this Cl here to generate here the resonance stabilized acyl cation. So this is our E+, the electrophile. The benzene ring reacts with the acyl cation in the rate determining step to give this benzenium cation, which, as you can see, is positive. If it's positive, any substituent here would have an effect on its stability. If the substituent here is electron donating, such as the methoxy, it will stabilize this, lowering the energy of activation for this RDS, making this reaction a fast reaction. So that's why this would be negative. On the other hand, if it were electron withdrawing, you could see that it will destabilize this, making the energy of activation for this RDS much higher and a slower overall reaction. So, as I've explained here, if we have a methoxy group which is electron releasing, it stabilizes this intermediate here. So you may recall from the Hammett plot or the linear free energy, if there is a negative slope where we have here the log of the rate constant here, and we have sigma values here where this is electron donating, such as OCH3, and over here this is electron withdrawing, such as the NO2. You can see that the OCH3 will have here a faster rate in the RDS, and an NO2 here would have a much slower rate because it is destabilizing this type cation here. So this is the rate determining step to create this in the RDS, and in the fast step here we get our product, or we get back our aromaticity here and our final organic product. So to conclude, this mechanism is consistent with this experimental observation here of rho value of negative and a large value because of the intermediate here that's generated is positive, and as we've said, electron donating groups here stabilize that intermediate, making for a faster reaction, and electron withdrawing groups such as the NO2 destabilizes this intermediate, making for slower reaction in the RDS and slower reaction overall. Let us look at another concept that's very important in organic chemistry: kinetic versus thermodynamic control of a reaction. The example that we'll use here is the electrophilic aromatic substitution of an aromatic compound known as naphthalene. As you can see from naphthalene here, all the hydrogens are not equivalent. We have these hydrogen known as the alpha hydrogens, which are close to or next to the bridge, the combination of the two aromatic rings here. There is the beta hydrogen over here, which are further from that junction. So we have the alpha hydrogen closer to the ring junction here. So we have 4, and there are 4 hydrogens which are further. Since they're not equivalent, if we react with an electrophile E+, we will still get an electrophilic aromatic substitution, but we can have a substitution in the alpha position as shown here, alpha substitution, or we can get a beta substitution for this as shown here to give the beta substitution. So these are 2 different products. Oftentimes in organic chemistry, as we know, we need one of these products as the major organic product. So the reaction conditions for this reaction, or reactions of this type, can be controlled to produce either one, the alpha as the major product or the beta substitution as the major product. Let us look at that concept a little closer, or to explain that. So if there is this electrophilic aromatic substitution, as I explained, we get 2 different products. However, one is more stable than the other, and this is more stable in the beta position because there is less steric interaction between these groups here, the electrophile and the hydrogen. As we have defined, one definition of stability is getting groups furthest from each other. So there's space so that the electrons from these groups do not interact or get too close to each other, because electrons are negative and negatives don't want to get close to each other. They tend to repel. On the other hand, this electrophile here is close to this hydrogen. So therefore there is steric interaction here, making this alpha substitution less stable than the beta substitution. The more stable product here is known as the thermodynamic product. So keep that in mind. That's the stable product, the thermodynamic product, and of course being more stable because of less steric interactions here. Let us look at another concept. We know that the rate determining step for this reaction involves the electrons reacting with the electrophile to give these two possible intermediates. Using the resonance structures here, we can see that this intermediate is more stable than this one. How do we know that? Because we can draw another resonance structure putting this positive charge over here. Notice that this benzene ring is still existing, or this is still aromatic. By looking at this one, we cannot delocalize this positive charge unless we interrupt this aromatic structure over here. So this intermediate here is more stable than this one. So once again, what's the importance? Since this is the rate determining step, remember the rate determining step determines the overall rate of the reaction. If the rate determining step has a high activation barrier, it is slow. If the rate determining step has a barrier forming a less stable intermediate, more energy is required, so hence a slow reaction. If the rate determining step forms a relatively stable intermediate, less energy is required for its formation, hence the overall rate of that reaction is faster because the rate of the rate determining step is faster. So let's look at this in terms of a figure. As we said earlier, we use this concept a lot in terms of figures and diagrams to explain different concepts. So here are the reactants. They all have the same level energy because they're starting with the same reactant, the naphthalene and the electrophile. But one here is less stable and the other one is more stable. So as you can see here, the energy of activation in the RDS to form the more stable intermediate is less. The energy requires less energy than forming this one here. So as a result, at low temperatures, the reaction path will favor this product because there is less energy required to form this intermediate, to form this product. This is the fast step, so we need not concern ourselves about this step. The most important step is right here. If there is a high temperature, there is enough energy to form this intermediate because a lot of energy is required to get to this activation, this transition state, to get to this intermediate. This will go on to form here the thermodynamic product. So conclusion, based on this slide here, to form the kinetic product, low energy is required, low temperature. To form the thermodynamic product, higher energy, higher temperature, more energy is required. This next slide gives a more specific example. So at a low temperature, the sulfonation of naphthalene will occur in the alpha position, and that is the kinetic product because it's the lower temperature. At a higher temperature, to get to the less stable intermediate, the sulfonation of naphthalene occurs, and it will eventually give the more stable product, which is also known as the thermodynamic product. Conclusion: if you are carrying out this reaction, and this is the desired product, the kinetic product is the desired product, you would carry it out at a lower temperature. If this is the desired product here, you'd carry it at a higher temperature. Okay, let's go on to another aspect here. And this is a substitution reaction, an aromatic substitution reaction. In this case, however, it's a nucleophilic substitution. Don't forget, what we've covered before is an electrophilic, where we had an electrophile reacting with the benzene ring. Now we're looking at a nucleophile. You will recall that a nucleophile is a nucleus loving. It's a Lewis base. It has an unshared pair of electrons, at least one, and it could be negatively charged or it could be neutral. But the bottom line is it must have at least one unshared pair of electrons. The overall reaction looks like this. We have a leaving group here, such as a halogen, reacting with a nucleophile to give a substitution reaction where the leaving group leaves. As you can imagine, this is an extremely difficult reaction because we have electrons here and we have electrons here. So getting electrons to react in an environment where there are lots of electrons requires extreme conditions such as high pressure or high temperature or an extremely strong nucleophile here. So let us see how this reaction works. So the first mechanism that we look at is this. So it's possible for the leaving group to leave in a rate determining step to create here this phenyl carbocation, to create that phenyl carbocation. As you can imagine, this phenyl carbocation is not as stable, nearly as stable as your alkyl carbocation. This is sitting in an sp2 orbital, so it's not as stable. In addition, for this to occur, because this is a very strong bond here, this has to be an extremely good leaving group, typically a gas, because as you will recall from your Gen Chem course, if a gas is the product, the reaction is entropically favors, the entropy favors the product because more randomness from the gas. So this rate determining step can happen, but very difficult, requires lots of energy, but we can favor this if this leaving group here is very stable and in fact a gas. In the next step, as you can imagine, the fast step, the nucleophile with its electron attacks the phenyl carbocation here to form the product. Here's a classic example of this type reaction mechanism. It's called the first order nucleophilic aromatic substitution. Why first order? Because in the rate determining step, only one molecule is required or is used up. Here's the diazonium salt, the benzene diazonium salt. So as you will recall, this reaction is possible because here we have the CN as our nucleophile. This is our leaving group as a gas. So this reaction will occur by this mechanism known as the first order nucleophilic substitution, by that mechanism. But bear in mind, however, it typically or generally occurs because there's a good leaving group such as a gas. Let us look at another mechanism. This is the second order mechanism, which implies here that two molecules will have to come together in the rate determining step. So let's look at this reaction here. 2,4-dichlorobenzene. So here's the leaving group, and here is the nucleophile. I have electrons here, of course, and here is the substitution of the Cl for this nucleophile to give this as the product, and here is our leaving group. Leaving group is not as good as a gas, but a fairly good leaving group. Notice here that we have nitro groups bonded to this molecule. Why so? Because as we pointed out earlier, the electrons here are reacting with a benzene ring that's nucleophilic. So these groups here, which are electron withdrawing, pulls electrons from the ring, making this less nucleophilic and more likely for the nucleophile to attack on this carbon. Let's look at the mechanism a little closer. So here are the two electrons from the nucleophile reacting at this carbon. Why this carbon? Because this is an electronegative chlorine. This is a polar covalent bond, so this is partially negative, as you recall, and this is partially positive. It reacts here, and the tendency again for this reaction to go is because we have two electron withdrawing groups bonded to the benzene ring. So in the rate determining step, as you can imagine, it reacts here and these electrons go on to this carbon. As you can see here, this is resonance stabilized within the ring. And in the fast step, as you can imagine, these electrons come back in to liberate or to give off the leaving group, or the leaving group leaves in the fast step to give the product, the nucleophilic substitution product. Notice again it's second order. Why is it second order? Because one reactant, two reactants come together in the rate determining step. I should point out again, as I mentioned earlier, if you put electron withdrawing groups here, it facilitates the reaction. I want to point out, however, that these electron withdrawing groups are more efficient if they are in the ortho and or para positions of the chlorine or the leaving group. In other words, if it were here, you can give that a try. If it were in this position, the negative charge could not be delocalized into the nitro group. So it has to be either in the para position or the ortho position, so that the negative charge can be delocalized and stabilize that intermediate much better. Other electron withdrawing groups, as we have seen, are the cyano group, or of course here the acyl type group, which can pull electrons, as you can imagine, onto the nitrogen or the oxygen. So let us look here at another type of reaction that's been observed. Notice this is chlorobenzene. It does not have any electron withdrawing groups on it, yet under extreme heat and high pressure, if this is the nucleophile here, we can get a substitution of this chlorine for this OH to give phenol as the product, and of course Cl is the leaving group. Of course it's a salt because we have here sodium ion. So this has been observed. Another one that has been observed is this is now sodium amide. As you recall, that's a very strong base. Because it is such a strong base, we cannot use water as a solvent, so the solvent that's used here is liquid ammonia. Extreme temperature and pressure, the chlorine is substituted for the nucleophile, the amide, to give aniline here as the substitution product here, plus sodium chloride again as the, chloride here as the leaving group. What is unique about this reaction, however, is that if this carbon is labeled or isotopically labeled So it's carbon 13 as opposed to carbon 12. Carrying out this reaction here gives this as the product and this as the product. You would expect this to be the product because this is the substitution right here based on the mechanism that we've just described, the second order mechanism. But we have observed, however, that this is also a product and it's 50-50 equal. So the question now becomes, how do we explain these products here, where this is now on the same carbon as predicted, but it looks as if it's also substituting this hydrogen here to get that product, and the chlorine is also gone. So as chemists, we'll have to come up with a mechanism to explain this reaction. So let us see how we can come up with a mechanism to explain this reaction. It turns out that a unique intermediate has been proposed over the years, which is called the benzene intermediate. Let's see how that works. So we have here the amide anion, which is a strong base. It can pull off this hydrogen as a proton. So notice hydrogen as a proton. So we get ammonia. And then these electrons come in to form here. This would have to be a triple bond, while this leaves as the leaving group. So this is the benzene intermediate. As explained earlier or mentioned earlier, this is unique. Why? Because we have a triple bond as part of a six-membered ring. As you know from your undergraduate, this is an sp carbon and another sp carbon here. So you'd expect that to be linear. But in order to explain the experimental observation, this has been proposed. Why has it been proposed? Because as you can see here, the nucleophile can attack this carbon to give this intermediate, of course, in the fast step, and then this intermediate will react with the solvent to get this as a product. Likewise, it can react at this carbon to give this other intermediate, and this would react with a solvent to give this as the other product. So that explains how we can get these two possible products. Again, notice they're in 50-50 equal mixtures because of this symmetry around this CC benzene intermediate here, because there's a 50% of attacking this carbon from the nucleophile or attacking this carbon from the nucleophile. So that gives us here a 50-50 mixture, and it also explains why there is scrambling. So one aspect here, one important take-home aspect here, is that you should be able to utilize experimental results, or you should be able to utilize the content that we're covering here, the concepts that we're covering here, to explain different experimental results that you gain from your research in the research lab. I think this is the last slide, and yes, it is. So continue to study hard on this. Read up the material in your text, and before too long I'll post another video. I think the next chapter is addition reactions, but I'll get that posted shortly. Okay.